Thank you for the introduction. I'm Martin Bielak and I work at Polarization University in Olomouc. And today I'm going to talk about all fiber polarization measurement in a single photon level and ideally in a single shot measurement. Okay, polarization, brief motivation. It's key degree of freedom in many fields. For example, in quantum physics, it's the source of the information for quantum communication, key distribution, or in quantum computing. But in a classical world, we can use polarization degree of freedom in material science, for example, for detecting some tens in material or some uh, defects in structures, or in biomedicine, we can reveal some hidden structures in biological specimens, or for example, the cells which are uh, like the cancer cells has a different polarization behavior than the normal cells, so it can be used like a detection method also in this biomedicine field. But most of these measurements are connected with the challenging conditions. What does it mean? For example, usually it's light intensities, like that there is just a few photons which carry the information of the polarization buried in the noise. Or in the other hand, usually we want something like a high speed measurement. It means that in our detection window, there is just a few photon which we can measure. Or yeah, we can deal with it like with increasing the light intensity. But the problem is that sometimes we are limited by the intensity of our source, or on the other hand, we are limited by the um, damage threshold of our specimen. Of course, we can use single detectors, but in the problem is that it's a relatively bulky thing, and sometimes we have space constraints. It means we are limited with the shape of our device, for example, in endoscopic measurements or something like that. And these constraints lead us to develop our all fiber polarization analyzer. This is a scheme of it. The main part is this few mode fiber, which is followed by a fiber array, and this signal is then detected by single photon detectors and analyzed by machine learning. Okay, let's look closely at this scheme. Uh, when the light is coupled in the few mode fiber, these modes starts to interfere each other, and at the output of this few mode fiber, the spectral pattern is created. This spectral pattern is polarization dependent. It means that the specific shape of these light and dark points is connected with the specific input state to the few mode fiber. The problem is that we can capture it by the CCD camera or something like that, but the detecting this spectral pattern by the single photon detectors might be challenging because of the number of points. But the technique we used is pair sampling by the fiber array. It's like, in our case, 7 fibers which precisely pick up 7 points from the spectral pattern, and then this intensity signal is brought to the single photon detectors, uh, and at, at the end we end up with the 7 numbers from the measurement. Okay, these 7 numbers are connected with the POVM elements created by this fiber array, but we don't know exactly which POVM elements it is. So we used a neural network to detect these quantum states, and in final step, we have these detections, and at the output of the neural network, there is the full density matrix, which describes the quantum state at the beginning of the few mode fiber. We used bunch of the polarization states for learning the neural network, and the neural net or the sensor is capable to uh, detect also pure polarization states as well as the partial polarized states. And as you can see on the right, there is a dependency on the repetition rate. You can choose between various scenarios. For example, for repetition rate 33 hertz, which is the repetition rate of human eye, the average fidelity of the detecting polarization states is higher than 99.9%. Or on the other hand, you can detect more than 2000 polarization states with fidelity higher than 99%. Of course, you can ask how many channels do you need for the measurement. So we tried to reduce these channels, like the points which we pick up from the spectral pattern, and you can see that with the sedum channels, the polarization measurement is quite precise. Then we moved to some practical realization. First of all, we did the scan point by point of a resolution test, and we found out that this all fiber sensor resolution is 6 micrometers. Then we moved to the measurement of dense connective tissue. On the left, you can see the intensity scan of the dense connective tissue, and on the right, there is a polarization sensitive scan of the same region of the tissue using our sensor, and you can clearly see that there is a hidden perpendicular structure in it which can't be revealed by the normal intensity polarization intensity measurement. Okay, that was like the scanning technique, which can be done like the by the rotating of the polarization wave plates or something like that. But you can imagine that you have your sensor. There is the micro channel in front of it, and for example, the atoms can float in front of the sensor, and you can measure it during the movement. And as you can see, there is a big difference between the measured polarization state when there is no datum and when the datum is floating in front of the sensor, and you can distinguish between the different type of datums, or also you can count the number of datums or something like that. But you can modulate the speed of the moving, and it's really not like a high speed measurement. So the last thing which we did is a measurement of the transition effect of liquid crystal displays. You can find them in every device which has a display and the thing is that these twisted nematic liquid crystals change their orientation when the electric field is applied to the electrodes, and this change is quite quick. In this case, it's took like 50 microseconds, and the key role here is like that we need to measure in each point to measure the polarization in single shot measurement, because you need to pick the whole statistic from the single point. And as you can see here, uh, we measured relatively precise and sample this transition effect with the good sampling ratio, and that is like it shows that the sensor is capable of the real-time measurement with a high repetition rate. And the biggest issue of the using multimode fibers is its stability. but thanks to using just a few mode fiber which supports only 10 modes and using only short piece of the fiber, we were able to achieve month-long stability. Okay, that's it. The sensor is capable to the single photon sensitivity and single shot polarization measurement, and the design is feasible for constrained spaces. I wanted to thank to our team, and there is a preprint on archive, and that's it for me. And if there are any questions, I'll be happy to answer them.
Thank you very much. Questions? I have a question related to,
Okay.
no, you use the a neural network, so which for the training, so which kind of is pattern recognition, some standard
It's a fully
classification?
connected neural network, and yeah, we measured the bench of the tested state, trained the networks, and then we used the unobserved states to test the quality of the
So
network.
that you can use also in this single shot.
Yes, exactly.
And so this is not, I mean, just you need the first training at the beginning and not nothing
Yeah,
else
we need
anymore.
the training set at the beginning, but it's like, you measure them at the beginning, and then you have this month-long stability to use the device
Okay.
without training the network.
Thank you.
You're welcome.
Further questions?
Thank you for the very thank you for the talk. I also have a question on neural network. So, how do you train it?
Yeah, thank you for the question. We measured 30,000 of quantum states, like the prepared states, and used the device, the all fiber sensor, to measure these 7 count rates. And this combination, like the quantum state at the beginning of the all fiber sensor and these 7 count rates, were used like the combination to training the network. And yeah, there was the training step, and then we measured a different combination of the input states and the statistic, and use this as these to find out the precision and how the training was successful or not.
Then, like, how do you parameterize your prepared state?
You mean the quantum state at the beginning of the fiber? Yeah, we use the density matrix, so it's like the full information of the quantum state.
I mean, the parameters for parameterizing the density metrics,
Uh,
or I mean, like density element, or just metrics element.
yeah, we use the
Okay.
whole matrices, so we
Okay.
can pick up any element of it,
Uh,
or you can transfer it to the Stokes vector or something like that. Basically, we have the full information of the quantum state at the beginning, also at the end of the fiber. So
Thank you.
that's it.
Okay.
Yeah, thanks.
Okay, thank you. Let's thank the speaker
Thank you.
again.